probably written code that works perfectly on your laptop, runs fine on a small dataset, and then completely falls apart when you put it in production. Not because of a bug, not because of a bad server, because of the algorithm underneath. Today we are going to talk about why that happens and the tool engineers use to predict it before it ever becomes a crisis. This is big O notation, and by the end of this, you are going to read it off any function in about 60 seconds. Here is the core question. Binary search finds a record in 1 million rows in roughly 20 steps. Linear search, scanning row by row, takes up to 1 million steps. Same data, vastly different algorithms. Big O is the language we use to describe that difference. It is not about how fast your CPU is. It is not about whether you are running Python or Rust. It is about how the cost of an operation grows as the input gets larger. Double the input, what happens to the work? That is what Big O tells you. Before we go further, let us be clear about what Big O ignores. It ignores constants. O of 2n and O of n are treated as the same class because at massive scale the constant disappears. It ignores small inputs. If you are processing 10 records, almost any algorithm works. Big O is a description of behavior at scale. What happens when n reaches 10,000, a million, or a billion? Engineers care about this because choosing the wrong complexity class is a problem that no amount of hardware can fix beyond a certain point. Let us walk through the 6 complexity classes every engineer needs to know. First is O of 1 constant time. This is the gold standard. Hash table lookups, array index access, retrieving from a cache. The cost is the same whether your dataset has 10 items or 10 billion. Second is O of log and logarithmic. Binary search is the canonical example. Every step has the remaining search space. 1 million items takes about 20 steps, 1 billion items takes about 30. The growth is so slow it is nearly invisible. Third is O of n linear. You loop through every element once, finding the maximum in an unsorted array, reading a file line by line, basic traversal. Cost scales directly with input size. Fourth is O of n log n linearithmic. This is where efficient sorting algorithms live. Merge sort, heap sort, tim sort, the algorithm that powers the sort function in virtually every language you use. Fifth is O of n squared quadratic. Nested loops. Every element compared against every other element. Bubble sort is the textbook example, but naive duplicate detection, certain graph algorithms, and poorly written join operations can all land here. This class is survivable at small scale and catastrophic at large scale. Sixth is O of 2 to the n exponential. Brute force search over all subsets, the naive traveling salesman solution, recursive Fibonacci without memoization. These algorithms are only usable when n is small, typically under 30 or 40, because the operation count explodes so fast that no machine can keep up. Now let us look at the growth curves visually. At n equals 100 the differences look manageable. O of n squared needs 10,000 operations. O of n log n needs roughly 700. But at n equals 1,000 O of n squared needs 1 million operations, while O of n log n needs 10,000. By n equals 1 million, O of n squared needs 1 trillion operations. No server on Earth processes a trillion operations per query in acceptable time. Meanwhile, O of n log n needs about 20 million operations, fast enough to run in milliseconds on commodity hardware. This is why algorithm selection matters more than infrastructure spend once you are past a certain scale. You cannot hardware your way out of a quadratic algorithm in a hot path. Now let us ground this in real engineering decisions you will recognize. The first is database indexes. When a database has no index on a column you're querying, it does a full table scan O of n, reading every single row. Add a B-tree index and the query becomes O of log n, traversing a balanced tree structure. 30 steps to find a record in a billion-row table. Add a hash index and certain equality lookups become O of 1. This is not a database tuning trick. It is a direct application of complexity theory. The second example is social feed ranking. Naive approach that compares every post against every other post to determine ordering is O of n squared. At 10 million users with active feeds, that is completely unusable. Real feed ranking systems use priority queues, min or max heaps, which are O of n log n structures, pulling the top k posts in linear time. Some systems pre-compute and fan out results at write time, trading write cost for O of 1 read cost. Every one of those decisions is a complexity trade-off. The third is autocomplete. Scanning every word in a dictionary for prefix matches on every keystroke is O of n times the length of the query. Unusable beyond a few 100,000 terms. Try data structures solve this. Try lets you find all words with a given prefix in time proportional only to the length of the prefix, completely independent of how large the dictionary is. That is why autocomplete feels instant even across vocabularies with millions of entries. Big O is not only about time. Every algorithm has a space complexity too, and it follows exactly the same notation. O of 1 space means the algorithm operates in place using a fixed amount of memory regardless of input size. Selection sort, two-pointer techniques, and many-bit manipulation tricks operate this way. O of n space means the algorithm needs auxiliary memory proportional to input size. Merge sort needs a temporary array the same size as the input. Breadth first search stores the frontier, which in the worst case can be proportional to the width of the graph. Memoization tables store one result per unique subproblem. The critical insight is that time and space are a trade-off. Dynamic programming is the canonical example. It transforms an exponential time algorithm into a polynomial time algorithm by accepting polynomial space. That trade is almost always worth it, but you need to know your constraints. If you are running on a machine with 8 gigabytes of RAM and your algorithm needs O of n squared space, you will run out of memory at around 100,000 elements. There is a subtler form of analysis called amortized complexity, and it explains something that trips up a lot of engineers. Appending to a dynamic array, Python list, Java ArrayList, C++ vector, appears to sometimes be O of n because when the array runs out of capacity, it copies all existing elements to a new larger allocation. But those expensive copies happen rarely. The array doubles in capacity each time, so a copy at size n prevents the next copy until size 2n. If you spread the cost of that one expensive operation across all the cheap appends that led up to it, the average cost per append works out to O of 1. This is amortized O of 1. The same principle applies to hash table resizing, union find with path compression, and splay tree rotations. The individual worst case can be expensive, but the long-run average per operation is cheap. So how do you read big O off a piece of code you have never seen before? Start with loops. A single loop over the input is O of n. 2 nested loops over the same input is O of n squared. 3 nested loops is O of n cubed. Then look at recursion. Count how many recursive calls each invocation makes and what work each call does. Fibonacci makes 2 calls and does constant work, so it is O of 2 to the n. Binary search makes 1 call on half the input, O of log n then drop all constants. O of 3 n plus 500 simplifies to O of n then drop low order terms. O of n squared plus n simplifies to O of n squared. At a million items, n squared is a trillion and n is a million, n is noise. Finally, check your built-in operations. In Python, list.sort is O of n log n. Dictionary lookup is O of 1 average. Checking membership within on a list is O of n on a set, it is O of 1. These matter enormously in tight loops. The right algorithm class beats any hardware upgrade at real scale. An O of n squared algorithm running on the world's fastest server will lose to an O of n log n algorithm on decade-old hardware once n gets large enough. Understanding big O is not academic. It is the difference between code that scales and code that becomes an incident at 3 in the morning. Learn to read it, apply it early. It will save you more time than any optimization you could do after the fact. One final thing worth saying, big O is a worst-case bound, not a guarantee. O of log n algorithm that has a terrible constant factor can lose to an O of n algorithm on small inputs. A hash table is O of 1 average but O of n worst case when everything hashes to the same bucket. The notation tells you the asymptotic shape of the growth curve. It does not replace profiling. Measure first, understand the shape of your bottleneck, then apply the right algorithmic tool. Big O gives you the vocabulary to reason about scale before you are in production. Profiling gives you the evidence once you are. You need both. This has been SysSketch Systems Visualized. Subscribe for more deep dives into the engineering ideas that make production systems work.